Today we will move forward towards full quantization of the scalar field and try to see what kind of states and expectations value for various things we do get from the quantization of the harmonic oscillators for each k mode and then summing it over to obtain the full field. So recall we had obtained the Hamiltonian of the scalar field to be harmonic oscillator like up to absorption of certain coefficient which we wanted to know, and the commutator relations between ak and ak dagger. So remember, a of minus k was also equal to ak, and a of minus k dagger was also equal to ak dagger. This was true because of the reality conditions of the field. So ultimately we do have up to certain constant c h square by 2, we have a structure which is almost like harmonic oscillator. We have h bar omega k, an extra c square is there which I can pull out here, and then ak dagger ak plus ak dagger. This kind of structure is there. If you recall, that was also present in the harmonic oscillator business as well. So if we quantize ordinary harmonic oscillator, at the end of the day we do get the Hamiltonian almost like this. But there the commutators between ak and a dagger, in quantum mechanics there is no k dependency in a, so a and a dagger was identity. Using that we converted this into ak dagger ak plus, actually it becomes twice of this, plus identity 1, and the outside half makes everything into single times of ak dagger ak and 1 by 2. So similar kind of thing we can expect if we do have the commutator between ak and ak dagger of a similar kind. So that is what we will try to see. How do we get it from? So first of all, recall what we had done. We had identified the dynamic field phi. We obtained its conjugate momenta pi by just going to the Legendre transformation trading phi dot 4 pi. And then the usual structure of a Poisson bracket structure should suggest me that there should be a phi and pi Poisson bracket which should be identity. Okay, this is particularly you have seen that in quantum mechanics or even classical physics of particles, if the dynamical variable is q, p is identified as del L upon del q dot, and then you have a structure like qp is equal to identity, not identity but 1. In classical mechanics it is 1, and this Poisson bracket later on is converted into commutators. When you convert the q and p into operators in phase space, the Poisson bracket becomes commutator and right hand side becomes iota h bar. Okay, now suppose there are two particles. Classically, let us say q1 and q2. So I would have a q1 p1 and q2 p2. Then you would have structure like qi pj should be equal to delta ij. That means q1's Poisson bracket with p2 should be 0. It should be non-zero only with p1, and vice versa. q2's Poisson bracket should be non-zero only with p2, and with p1 its Poisson bracket should be 0. So that is captured by delta ij. Okay, if two particles are there, jointly their Poisson bracket is written like that, and therefore jointly their commutator would be written like this: qi pj is equal to iota h bar delta ij. So you see, each particle knows about whom to commute and whom not to commute with. So this is relevant because in field theory we do not have one oscillator, we have hundreds and infinitely many of oscillators because of the k dependence. For each k we have an oscillator, and therefore each case k should know about whom to commute and whom to not commute with. Even in the position space we have different operators at different positions. So there is so if this is a position slice, then here there are some operators phi here and pi here, and similarly some other location there, phi there and pi there. So this will be function of x2 and this will be function of x1. So therefore this phi should know that its Poisson bracket with respect to this position should be non-zero, and with respect to some other position it should be 0, and vice versa. So ultimately, in the same spirit of multi-particle structure of Poisson bracket or commutator, we should anticipate the phi and pi commutator should have this delta function behavior, that it only becomes non-zero for the same point. And since it is a continuous variable, Kronecker delta ij, which was true for Dirac for a continuous discrete variables, is getting replaced by Dirac delta function, which does not become 1 at its argument 0 but shoots up to infinity at the cost of shrinking its width. So Dirac delta function is the continual generalization of the Kronecker delta. So we expect phi and pi to have this kind of Poisson bracket from its structure. Okay, so let me erase this and make it clean space so that we can clearly see where we are headed. So this is what a natural phase space structure converted into commutator should give me. And I know this delta function can be written as a Fourier integral of x minus y. So delta function is known to be d3k, it should be k here, d3k e to the power I k dot x minus y. So this is what we should be able to obtain. And since we know phi and pi individually can be written in terms of ak and ak dagger, which we previously did, this boxed equation, phi and pi can be written like this. So I will feed the information of the whole phi here and feed the information of whole pi there into the commutator and try to recover what is the commutation relation between ak and ak dagger and so on. So that's what I do. This h bar cube to the power divided by iota c will come from root h factor, which was coming from phi, and remember pi was coming with root h times h square by iota c. So together they will give you this h bar cube iota c kind of thing, which is outside. Then inside I will write down all the operators with their coefficients. So this is the operator description for phi, and this is a operator description for pi. Each one of them is an integral over all k's. So I have written two different k integral and k prime integrals. Operators part are only ak's and ak daggers. So these are the operators. Okay. Remember, each of ak comes with e to the power minus I omega t or minus I omega k prime t here, but each of ak daggers come with plus e to the power plus I omega t. Okay. So now this is the structure. Operator parts here are only ak. So commutator will have four kind of term. When this goes and tries to do a commutation with this one goes and tries to do a commutation with this with a negative sign. This one goes and tries to do a commutation with the first, and this one goes and tries to do a commutation with the last term over here. So ultimately you will get four terms. Their exponentials in the time will combine in that particular way, and in their exponentials in the position will also combine in that particular way. Okay, so this should be fine enough. You should just write it down, collect all the commutators, and you will get the next equation, the big curly bracket equation here. So this is what phi pi commutator at equal time. So this is at equal time. Remember when we did commutator of classical particles as well, the q and p are supposed to be at the same time, then only it becomes iota h bar. If q is at time t1 and p is at time t2, then you do not get iota h bar. So this is called equal time commutation relation. Equal time commutation relation, which also gets a short name ETCR. So times have to be the same. So you see the coefficients of both omega k and omega k prime are the same because we are talking about same time, but we are not talking about the same position. So therefore coefficients of k and k primes are different. Okay. Now one more thing I would do before going ahead, I would just do the integral d3k prime is also there here. What I'm going to do is a variable transformation. I'm going to relocate each k prime into minus k prime. So you know the integral measures would not change. So if d3k was running from minus infinity in all its component kx, ky, kz, it will go into d3 again, remain the same with a minus sign. Let us call it k double prime. So then it also becomes the same thing. So the measure does not change under this redefinition. Omega k does not change because it is not sensitive to the signature of k. It becomes k square. And we know ak and ak daggers are also symmetric under k going to minus k. So nothing will change up to the last term here. Only here k primes will become negative. All other terms will remain the same. Nothing changes under k going to minus k. So ultimately you will have exponential e to the power I k dot x minus iota k prime y. So overall factor of all the four commutators, the spatial part, previously they were all plus k dot x plus k prime dot y. Now under redefinitions of k going to minus k, it will become e to the power I k dot x minus I k prime dot y. Okay, so this is what you would get. Now let us try to compare things. I want answer should be iota h bar times integral in d3k times e to the power I k dot x minus y. First of all, there is no time dependency. It should be true for all time. So the time argument of this phi and pi should be the same, but that time argument could be anything. It could be t equal to 0, 25, 30. The answer on the right hand side should not change. So it should be time independent. So first of all, I will try to locate and try to see how the time elements could be taken out. So you see time appears here, time appears here, time appears here, and time appears here. So you see in the last two terms, in this and this, time dependency can be taken out if omega k is equal to omega k prime. Then this portions will drop off. So from here I want to have delta k primed. If they become the same thing, then the time dependency in the last two terms goes away. But look at the first two terms, omega k plus omega k primed, that can never be set to 0. Time dependency cannot be killed because omega k cannot be equal to minus of omega k primed, because omegas are positive quantities. They are square root of k square c square plus m square c4 upon h square. So therefore there is no way by selecting omega k and omega k prime I can kill this term. So only way this term can go away if the commutators they are getting multiplied with, they go out, they become 0. So ultimately the demand which we should have is that this omega k and omega k prime should be same, which demands k and k prime should be the same, and then these two terms will lose their time dependency. For first two terms to lose their time dependency, only their commutators need to vanish. There is no other way. So ultimately the demand of time independency will force me to have this ak commutator to be 0. This should be 0. This should also be 0. And these two terms are roughly the same thing with a flip of a minus sign. So remember, here I had a plus over here. So here I should have a plus here. I had just flipped ak dagger, ak prime was, ak dagger commutator ak was there. So I just flipped their order to obtain in a similar kind of structure. So you see, if both of them become the delta kk primed, the time dependency goes away, and even the exponential, I had e to the power I k dot x minus k prime dot y. With a delta kk prime, this will also become e to the power I k dot x minus y, something which we were looking for. So in order to obtain the proper commutator, the commutation relation set which I have got should be this boxed equation. This equation over here I should get. So now once these commutator relations are with us, we can go back to the Hamiltonian and try to find out how does the Hamiltonian change. So remember, there is an extra c upon h square factor we want in the commutator, because that has to cancel this h cube upon c factor to leave us with h bar factor outside. So we wanted just a iota h bar factor outside. We are getting iota h bar cube upon c. So therefore this c and h bar square which are coming extra should be adjusted by the commutator. They should envelop that to get us the correct thing. So we have this relation therefore at our hand. If that is the relation, that means ak AK dagger should be equal to this commutator value, which is C h bar square times delta of 0, because when I put k is equal to k prime, I will get a delta of 0 plus AK, sorry, so I should have written, so this is fine, plus AK dagger AK. Okay, so this is what I would get. So therefore, we can, in the Hamiltonian which we had obtained previously, AK dagger was appearing over here. To this, I would just write down C upon h bar square delta 0 and AK dagger AK. So that is what I will get, twice of AK dagger AK and C upon h bar and delta of 0. Okay, so therefore, from outside, as we discussed, this Hamiltonian had the structure, if you remember, Hamiltonian had a structure which was outside we had a, so we have to go a couple of steps back to just look at where we had, here it is. The Hamiltonian had outside C h bar square by 2. So that C h bar square by 2 would be remaining. Just a second. Right. And this C square we had pulled out. So we had C h bar square upon 2C square. Ultimately outside I have a h square by 2C. So that's what would remain outside. And inside I will get twice of AK dagger AK plus C upon h bar square delta 0. Now the time is there to bring this whole factor inside. If I bring the whole factor inside, here the 2 will cancel each other, h square by c will be remaining with AK dagger AK and plus delta 0 will be obtained. So you see, this will become our Hamiltonian. For it is almost like harmonic oscillator. Each harmonic oscillator has this much energy. This is the number operator for each k, and instead of 1 I am getting a delta 0, which is a theory, which is the artifact of a continual theory. Continuous theory would have delta k minus k prime. Kronecker delta will be replaced by a Dirac delta. It's delta 0 will come about. And then I have a d3k summation over all such oscillators in momentum space. So only thing is just that this h bar square by c might be troubling you. So what we can do, we can absorb it in the redefinition of various things. For example, I can redefine the field as phi tilde as root c times h bar phi. So if remember, if that we did, our Lagrangian which we started with was also containing a minus h square by 2 times c, and this was the Lagrangian. If I do this redefinitions of thing, I will get this c times h bar square absorbed in phi, and I will get a phi tilde everywhere. So extra factor outside, not 1 by 2, this c h bar square factor can be absorbed into redefinition of phi. Then you can get a redefinition of pi, which is a conjugate momenta. So phi will go to phi tilde, pi will go to pi tilde. Then things will start coming into order. You would get phi tilde as this, because previously you had this much for the usual phi with a c will come. So extra root h upon c, extra h upon root c will come about. So this h and root c will be extra compared to the previous definition, and similarly for pi as well, this h bar and root c will be extra after absorbing the outside factor. So you will get this kind of new phi tilde and pi tilde. And in the same spirit, as we rescale the phi, if I rescale the AK and AK dagger absorbing these coefficients, I will have a tilde k, which is just the same factor multiplied to previous AK as the new phi gets defined after absorbing these factors into phi. If I do in this all things, that means I absorb this root c times h bar everywhere. The correct phi and pi tilde in terms of their AK tilde and AK dagger tilde would be exactly like harmonic oscillator without any extra h bar or c factors. So all those things I have absorbed, and the Lagrangian becomes simple enough. And Hamiltonian in that case would be exactly like harmonic oscillators thing without any troublesome factor of h bar square by c. So I could have started the story with absorbing the phi. So I have just showed you a way where you start with a general phi, and then you land up on to a harmonic oscillator up to a constant coefficient that you can absorb. And overall, in many textbooks, actually, you will find this thing being told from the beginning with a mysticism called something called a natural units. So we are very close to that we have absorbed h bar and c as much as possible. Not completely, we could have absorbed even c's appearing here and there into this. And most of the textbooks tell you that they are going to write down something called h bar is equal to 1 and c is equal to 1 units. That means they will not care presence of h bar here and presence of c there. But still, if you want to focus that you want to keep all h bar and c together, a good set to do business would be this Lagrangian, where we have ate up the extra h bar square c factor coming from outside, and this pi phi pair, which is just like harmonic oscillators. And lastly, you will get exactly the same commutator between ak and ak dagger, just like a ordinary harmonic oscillator which we had done previously. And therefore the Hamiltonian will become just a collection of all oscillators put together. Only signature of this being a continuous theory is the appearance of this delta 30 rather than a 1. So in harmonic oscillator case, remember this function which is appearing apart from the number operator counts the state of the energy of the vacuum state. Suppose there was a vacuum state for oscillator, there you knew that even for vacuum state there is an energy which is obtainable from half factor. So half h bar omega is the energy of a vacuum state. If you excite further, this ak dagger ak adds particle to this, which each come with n h bar omega, how many particles you have excited. The same game is appearing over here. This infinite delta 0 is actually the energy of the vacuum state. And then you are summing over all vacuum of all of these things in a continuous theory will give you infinite amount of energy. And over that, the finite part is the excitation energy coming from the excitations of particle. This counts, this number operator times h bar omega counts the excitation or energy excitation above the vacuum energy, just like it did for harmonic oscillator. Only thing of the interest or change here, for a continuous theory, you are getting an infinite as the energy of the vacuum compared to a finite half, which was previously present. Okay, so now we will go further and try to identify the existence of such a vacuum and how to identify different particle modes which can exist over here. Okay, so again we will start the story similar to the harmonic oscillator case. We will assume that suppose there is an eigenstate of a Hamiltonian, and then we will try to see what does ak and ak dagger do, where do we that takes us, and what kind of states are generated. So remember, we have a harmonic oscillator structure for each k mode, and we have a commutator structure just like a analog of a ordinary oscillator with the delta function appearing this time rather than a Kronecker delta. Now let us assume that psi of k is an eigenstate of Hamiltonian at k. Remember, we had identified Hamiltonian as d3x of Hamiltonian density. Total Hamiltonian was integration of Hamiltonian density d3x. The same thing can be written as a d3k hk as well. So total Hamiltonian can be written like this as well. This is an exercise for you to find out what is the expressions of hk, and actually you can see hk is nothing but the harmonic oscillator. This is your hk. Okay, so now we have a Hamiltonian for each k. This is like a harmonic oscillator for each k. Therefore, there should be eigenstate for each oscillator as well, and these are the eigenstates for each oscillator, psi k. And let its eigenvalue be lambda k. So that means the hk acting on psi k should give you back lambda k psi k back. In the definition of hk, already there is a trivial part. Trivial part in the sense of this delta 30 times half does not come with any operator. That means it is coming with identity operator. So that part acting on psi k will give you psi k back. So that is eigenstate part is respected by that term. The only non-trivial part is that the first number operator should act on the psi k and give back you state psi k with some eigenvalue times delta 0, let us say. Let us say this is the energy eigenvalue for this operator. Delta k times lambda k times delta 0. Okay, I am just redefining my eigenvalue to be lambda k times delta 0. Okay, this is my demand. So if that is the case, then total energy of the whole system should be lambda k plus half. So sorry, I have written a minus here and there. I do not know why, but let us see this. It should be okay. So the total energy in this definition, if I put that eigenstate of ak dagger ak gives you eigenvalue lambda k times delta 0, then the total Hamiltonian acting on the psi k will give me, first term will give me lambda k times delta 0, the second term will give me half times delta 0. So together combined I will get lambda k plus half delta 0. So this would be the total eigenvalue of the Hamiltonian. Okay, so I'm saying if I take eigenstate of ak dagger ak operator with eigenvalue lambda k times delta 0, then that state is also eigenstate of total Hamiltonian with eigenvalue lambda k plus half delta 0. All right. So now let us try to see what do we get. What do we get in terms of if I act ak operator on psi k. So let us see whether it acts as a ladder operator, raising operator or lowering operator or not. So first I take psi k primed and define it like this. And I want to know what happens when h of k acts on psi of k primed. What do I get? So there are again in h of k there are two pieces. One is half delta 0, which is trivial, that will give me the lambda k prime back with a half delta 0. Only non-trivial operation I have to be aware about is ak dagger ak acting on psi k primed. Psi k primed is ak times psi k. So there I can play the game that I would now have this ak dagger ak here appearing. I can flip it using the commutator into this AK. So a dagger k ak was appearing over here. I can flip it using the commutator as we had done in past as delta 0 ak ak dagger. Okay, so that is what I will get. So here, so I have in hurry I had changed the signature here as well. So here it should not change, only here last step it should have changed. Okay, all right. So using the commutator properly, I will get a ak dagger minus delta 0 would be ak dagger ak, which is coming from the commutator we just wrote above. From this commutator, when you put k is equal to k primed, you will get this relation over here. So I have flipped the left two operators into this, and ak, which was appearing over here, still survives like this. Now we go forward, there will be two terms, once this combining with this and then delta 0 combining with this. So first I will get three AKs, ak dagger, ak coming from this and this put together. Just let me clean it up so that we can see. So we will have 3 ak dagger and ak, which is over here, and then minus of delta 0 times this, which is fine. Okay, and we already know what does ak dagger appearing here times ak acting on psi k does. Ak dagger ak acting on psi k used to give me lambda k times delta 0. So that will still be maintained. Lambda k from here I will get lambda k times delta 0 and one ak will be left outside. Together that will become lambda k times delta 0 and ak acting on psi k, and from this side ak acting on psi k with a minus delta 0. So put together everything, I would have a lambda k minus 1 delta 0 with ak psi k. Remember ak psi k was defined to be psi k primed. Okay, So we had written somewhere, which I might have erased right now. So what happened when I operated AK dagger AK on AK psi k, I got back AK psi k with eigenvalue lambda minus 1 delta 0. That means AK has reduced the eigenvalue by 1. Only psi k was an eigenvalue with lambda. AK times psi k is reduced eigenvalue by 1. So therefore the Hamiltonian will also go down one step. I will get a lambda minus 1 plus half this time. Okay. And similarly, you can prove the just like harmonic oscillator. If I did for AK dagger the same business, you will realize that this time eigenvalues go up by 1. So what AK does, AK reduces the eigenvalue of psi k by unit 1 times delta 0, and AK dagger enhances the eigenvalue with unit 1 times delta 0. Only thing which might have been worrying you why I had taken delta 0 in the this definition of eigenvalue. This is because you see I have two AKs multiplying. 2 AK multiplying should give you something of the dimension of delta. It cannot be that left hand side is dimensionless quantity and right hand side is a dimensional. This is a Dirac delta in volume in a K space. Dirac delta in K space is like a dimension of volume, total volume. So this is what we should also get. After 2 AKs act, the state should not remain the state is whatever dimension of the state is there, it would give you the same thing. But extra factor here and extra factor here should have the same dimension. So if I call this as a real number, then something like a volume should multiply. That's why I have written a delta 0. Okay. So just to be consistent, I have redefined lambdas as lambda times delta 0. So you see, it doesn't matter. Ultimately, in this way, if I write, what happens? AKs take the states down by 1 units. AK daggers take the states up by 1 unit. So for each K oscillator, AK and AK dagger indeed behave as raising and lowering operator, and everything of harmonic oscillator comes true. And in the same spirit, just like for ordinary harmonic oscillator, if there exists a lowermost state, if the Hamiltonian is bounded from below, that is to say, if there is a minima of the energy, then at some stage AK's operation should act on that minimum energy state and give you 0. Because if it is not 0, some other state, I will know that it will be eigenstate of Hamiltonian with 1 reduced unit of delta 0 energy less, and then again acting on that, I will get one step down further and further and further. This process will only terminate once you hit a 0, not 0 ket. So 0, number zeros, that is the state which is completely annihilated by this. And I know this AKs go down by unit 1. In any case, it will be annihilated only if these lambda k's are integer numbers. Then only going down, I will hit 0 after few steps. If they were not integers, let us say 1.5 or something, I will never hit this 0 after even operating 10 times or 20 times. So two things are realized. There is an eigenstate with 0 eigenvalue, let us say, and that fixes that all other eigenstates of the Hamiltonian or number operator would have integer n's. Okay, so this is exactly like harmonic oscillator philosophy, which we had obtained. And therefore, we have just talked about one oscillator. If there are two oscillators, I know the total vacuum state is oscillator 1's vacuum and oscillator 2's vacuum. And now we are talking about infinitely many of them for each K. So the total vacuum of the full Hilbert space will be vacuum of first oscillator, vacuum of second oscillator, vacuum of nth oscillator, and so on. That is collectively written as a product K and vacuum state for each K. And the operators can be raised and lowered in each K segment by their respective AK dagger operators or AK operators. So you see, for each K, I can either have a 0K, which is a vacuum of that oscillator set, or I can have first excited state, which is AK dagger acting upon AK, or I can have second excited state while two AK daggers act on the vacuum, and similarly nth eigenstate or n plus 1th eigenstate by obtaining AK dagger acting on NK, and you will get just like an ordinary oscillator you will get this kind of structure. So this whole set of oscillator for each k exists, all set of states for each k exist, and you can have a superposition of that to write down a valid oscillator for that k mode. And the Fock space is defined as collection of all such Hilbert spaces of all k's together. Total Hamiltonian is oscillator number 1, oscillator number 2, oscillator number 3, and also oscillators put together. Their Hamiltonians are in direct sum, while their states are in direct product. So you see, you can have first oscillator in any of these states or their superposition. Second oscillator could be any of these states, this or that, or their superposition, and so on. So there can be possible states which are like vacuum of in all oscillators, or first oscillator is in first excited state, all other oscillators are in vacuum, or first two oscillators are in excited state, all others are in vacuum, and so on. Similarly, first oscillator is in second excited state, all others are in vacuum, or first two oscillators are in excited state, double excited state, and all others are in vacuum, or one oscillator is in double eigenstate, one is in vacuum, third one is again in first excited state, and so on. You can think of those infinitely many combinations. Each oscillator can have any of the eigenstate, vacuum, or their superposition, and similarly for all others. So this description is called the Fock space. There is a vacuum for each k, there is a Hilbert space of each k, and tensor product of all such states is called the Fock space. Okay. Lastly, we will just see how to do business with such states. First, we will want at least the vacuum state of the theory to be well defined and well normalized. That means normalizations of vacuum for each oscillator should be equal to 1. That we demand that for all k's, ground state should be well defined, let us say. If I do so, then I realize the first excited state do not remain very well defined. Why is that? Because first excited state is obtainable from operation of AK dagger onto vacuum. So this is first excited state 1k, this is its conjugate. When I take inner product between 1k and 1k, I will get this AK dagger in between. And this AK dagger using the commutator can be written as a delta 0 plus AK dagger AK. This is the usual commutation usage. And this AK acting on vacuum will kill it. So therefore this term will touch this vacuum and make it 0. Only this term will survive. So delta 0 is not an operator. It means there is identity here. Delta 0 will come out and 0k will get inner product with itself, and I will get a 1. So ultimately delta 0 will survive, which is not 1. It is not well normalized state. It is infinity rather. So that tells you exciting just a single photon with a single k is not a physical process. It cannot have a well-defined state. So just exciting a single k is just not possible. It is unphysical. It is not a well-behaved state. So therefore, what one should really look for, we do not excite at a particular k, but we have a width, some spread. I do not exactly know where I have excited. I can just say that I have excited around k value in some width. That width is given by fk. So I would have state that I do not know which k exactly it is. It is some k centered maybe around some k naught value, but some distribution should be there. And you can find out that such a state's norm is obtainable from the L2 integration of fk. So if fk's are L2 function, Lebesgue functions of order 2, then the states can be well normalized. So in order to have a well normalized state, the outcome or the cost one has to pay is that you do not claim exact knowledge of which photon of which momentum has been excited. You just say that most likely this photon is excited and there can be some width. This is something like uncertainty principle in some sense, that you do not have precise knowledge of momenta. That is barred from you. If you demand precise knowledge of momenta, then the wave will become plane wave in position space, and therefore you would not have normalizability. So in order to have a normalized state, you need to have some superpositions of k, and therefore your states in position space cannot be plane waves. So this is what is exactly replicated here as well. So lessons: scalar field have exact harmonic oscillator like structure for each k. H is harmonic oscillator for each k, product over all k's. So not product, sum over all k. Energy is sum over all k. States are like, you could have product over well-defined states in all k or summation of them. So let us say ck, kind of this. Okay, so this kind of superpositions in different k's and product over all things, just like we saw, it could be 0 on wave number 1, first excited state in wave number 2, and then everything else in vacuum, plus first two things are in vacuum, k1 k2, and nth ninth state is in third eigenstate, and so on. So all these things can be constituted and superposed with. Only thing is that different Hilbert space elements will be coming along. So those are the Fock space bases, and in that basis one can write down well-defined state by taking superpositions. So first, I will stop the discussion on scalar field here. First, we will try to get the similar kind of structure for other kinds of field. For example, a Dirac field as we discussed, and for photon fields as well. So we will realize the Fock space structure for all of them, and then we will, in the remaining week, remaining classes for field theory introduction, we will try to do business with states of our choices. Okay, so this is the structure, the Hilbert space structure of a field. It is like oscillator is momentum space or Fourier space, and every property of oscillator is more or less coming through with cleanliness. Only thing, a delta zero appears here and there that you have to be very careful with, because we are doing a continuum theory. Okay, so I stop here for scalar field. In the next class, we will start dealing with Dirac fields and see whether the same kind of Fock space structure comes about for Dirac field or not. And once we are through with that, we will do photon fields or U1 field, electromagnetic field. Okay, so I stop over here.